Today we're going to be reviewing states of matter, specifically gases. So the three states of matter that we will talk about, of course, are solid, liquids, and gases. Typically with chemistry, when it comes to calculations, most of what we will be doing has to deal with gases and their behavior. The reason that we focus on gases is in part due to the kinetic molecular theory. So this is an explanation of the behaviors of solids, liquids, and gases based on the behavior, the movement of particles. So kinetic, of course, means motion. This has to do with the kinetic energy of particles. And molecular, of course, refers to molecules, even though you do have some gases that could be atoms as well. So the kinetic molecular theory most accurately describes the behavior of gases. Ideal gases are gases that don't really exist. These are gases that would 100% follow what is stated for gases' behavior in kinetic molecular theory. Real gases are the ones that we actually deal with in the real world. They're not ideal, but they can be close depending on the conditions. So in normal conditions, their behavior is pretty close to ideal gases, but still not perfect. So there are 5 assumptions for ideal gases based on kinetic molecular theory. The first is that the volume of the gas particles, whether they're molecules or atoms, the space that they take up is basically non-existent compared to the volume of space between gas particles. So that means that the volume that we refer to with a gas is actually made up of mostly empty space. Gas particles are in constant random motion. They have a large kinetic energy, especially when compared to solids and liquids. Gas particles experience collisions that are elastic. That means they don't lose any kinetic energy after a collision occurs. Gas particles don't experience attractive or repulsive forces, meaning they aren't attracted or repulsed by other particles in the volume that we refer to, and a big reason for that is because they are so small compared to the volume of space between them. So the motion of one particle in that sample would be independent of the motion of all other particles in that sample. And finally, the average kinetic energy is dependent or related to temperature. So all 5 of these things describe ideal gases perfectly. When we have real gases, there are exceptions. So for example, real gases do experience attractive and repulsive forces with one another. They are less than the attractive and repulsive forces that are experienced in the liquid and solid phase, but they are still technically there. Some spheres of gas are larger than spheres of other molecules of gas. So we will go into a little bit of that, how real gases are different than ideal gases later on in AP Chem. So gas pressure, all pressure is defined as a force over area. For gas pressure, it's just the force that gas particles exert over a given area. Gas pressure is a result of collision of gas particles with the walls of a container, typically that they are confined by. If you were to increase the average kinetic energy of the gas, you increase the average speed of the particles. So when we think about a sample, we do refer to average kinetic energy because not all particles are going to have the same speed or the same kinetic energy. There are some particles that are going to have low kinetic energy and have a low speed, and some that are going to have really high. But on average, that's typically what we are talking about, especially when we refer to temperature. So the force being exerted on the sides of the container will increase if the average kinetic energy increases, because there are more times in a given area that those particles hit that container, which increases the pressure. Pressure and temperature do have a direct relationship because of this. So if we increase the temperature, we increase the average kinetic energy, which increases the number of collisions with the wall of a container, which increases the pressure of the sample. There are several units of pressure that you will see. Atmosphere, millimeter of mercury, which is mmHg, that refers to early barometers used to be filled with mercury, and then the pressure exerted would change the level of mercury in a tube. So that's where millimeters of mercury comes from. Torr, which is basically another word for millimeters of mercury because it's the same measurement. One's just named for a scientist and one's just based on the barometer, reading it, millimeters of mercury. And then there's Pascal or kilopascals typically. And then there's also pounds per square inch in the US. That's kind of like a US unit. So if you look in the information booklet they give you about your car, typically tire pressure is in PSI. So we can convert from one unit of pressure to another. Typically in AP Chem, you will see atmospheres or millimeters of mercury. I believe in the packet that you get on the exam, they give you this conversion, but 1 atmosphere is equal to 760 millimeters of mercury, or 760 torr. So these two units are equal to each other, which is equal to 101.3 kPa, kilopascals, which is equal to 14.7 psi, pounds per square inch. There's also atmospheric pressure. So typically gas pressure, we're referring to the pressure exerted in a sample of gas. Atmospheric pressure would be the pressure of the gases in the atmosphere on the surface of the Earth. So typically we measure this by a barometer, which again, early on, they had, it's basically like a bowl of mercury with a tube coming up. As you increase the pressure on the surface of the mercury in that bowl, you would increase the level of mercury in that tube, and that's how they would measure pressure. Higher altitudes do have lower atmospheric pressure. So if you think of the Earth's atmosphere, there are layers to it. So as you increase your altitude, you're decreasing the actual moles or number of gas particles that are exerting pressure. So if you reduce how much gas particles there are based on where you are in altitude, then that would lower the atmospheric pressure because there's less gas putting a force on you. For kinetic energy, again, we're relating average kinetic energy with temperature. So the kinetic energy of particles in a sample aren't always the same. So there are some that have a higher average kinetic or a higher kinetic energy, some with a lower kinetic energy, but we describe the temperature of a sample based on the average kinetic energy of all particles in a sample. So heat is a form of energy. So if we increase the amount of heat that we input to a system, we're giving that system more energy. That energy can just be absorbed by particles, or it can be used by particles to basically speed up their motion or increase their range of motion, which is registered as an increase in temperature. So this is what we're talking about when we talk about average kinetic energy. Here we have a blue colder sample and a red hotter sample. The average is the highest point of the peak. So here we have, even in the hotter sample, we have some particles that have very little energy, so they are pretty slow. But, there we go. The average, most particles have a higher energy than in the cold sample. So here, most of the particles are here on the x-axis. For the hotter sample, they're way over here. So there's a higher average kinetic energy, even though we still have particles that have a relatively slow or range of motion, small range of motion. Even with the cold sample, you have some particles with a higher range of motion that have more energy. So just because you have a cold sample doesn't mean all your molecules are slow. And then there's also absolute zero. So absolute zero is 0 Kelvin, which is equal to negative 273 degrees Celsius. So the Celsius scale is based on the boiling point and freezing point of water. Kelvin is based on the range of motion of particles. So at 0 Kelvin, that means that all particles have no motion. And it's a theoretical temperature. It hasn't actually been achieved in the lab. It's just like a concept. So if you think about like 100 degrees Kelvin versus 200 degrees Kelvin, at 200 degrees Kelvin, those particles have twice as much energy as particles with 100 degrees Kelvin. So Kelvin is based on the motion of particles. Absolute zero is therefore 0 Kelvin, where the motion of all particles theoretically stops. So even with solids, way in the beginning, I have a little GIF that describes the motion of particles. So even in solids, particles do have motion. At absolute zero, no particles would be moving. It's like a still picture. So that's our quick introduction to gases. Next we'll be talking about liquids, but let me know if you have any questions.